Let's study magnetic field at a point on the axis of a circular current carrying coil, and the structure under the drawing will be consider a circular coil of radius A, center is at O, and current I is flowing in the anticlockwise direction through the coil, and P is a point situated on the axis of the conductor at a distance x from its center O. This point is P. Then consider a small section dl of the conductor at M. Let's join the point P and M and take the distance as r, and the angle between r and x, let's take alpha, and here angle between dl vector and r vector, that means this is theta. As it is a 3D structure, so the sine theta or theta is 90. Here theta is 90, and in this small section magnetic field due to this section at point P will be dV equal to mu 0 by 4 pi IDL sin theta by r square. Here we are using the Weier's law. According to the Weier's law, dV equal to mu 0 by 4 pi into IDL sin theta by r square. As here theta is 90, so sin 90 is 1. So dV will be mu 0 by 4 pi IDL by r square. And direction of dV will be directed along PQ. We know the direction of magnetic field is perpendicular to both dl vector and r vector and can be determined by right hand thumb rule. So direction of dV will be in this direction and it will be in PQ direction. And if we divide dV into its sine or cos component, then we get that become cos component and that becomes sine component. As here this angle is alpha and it's also 90, then it becomes 90 minus alpha, and here dV and r vector makes 90 degrees, so as it's 90 minus alpha, it becomes alpha. As this angle is alpha, so we get dV cos alpha and dV sin alpha. Similarly, if we consider a diametrically opposite section dl at M dash, this direction will be in at point M dash, then this also makes angle alpha and dV dash and dV dash cos alpha, this angle also alpha, and that's become also dv dash sine alpha. From this dv cos alpha and dv dash cos alpha, then these are equal and opposite, so they cancel out, and finally we get dv cos alpha, dv sin alpha and dv dash sin alpha. So net magnetic field intensity at V due to the circular conductor will be V equal to 0 to 2 phi a dv sin alpha. Here we have to put the value of dv and the value of sin alpha. From the figure we can get sin alpha. Here this angle is alpha. From the triangle M, O and Phi we can get sin alpha. Here sin alpha is equal to A by R, and dv we have get that dv equal to mu 0 by 4 phi into I dl by r square. From that we can get dv equal to integration from 0 to 2 phi a mu 0 by 4 phi I dl will divide by r square into a by r, as mu 0 by 4 phi is constant and current flowing is also constant, and a is the radius of the circular coil, that's also constant, and r is the distance from the point M to the point Phi, which is present on the axis of the circular conductor, and that's also constant. So dl is that which we have to integrate. Then we write mu 0 by 4 phi into I a divided by RQ into integration from 0 to 2 phi a. Then integrating we get mu 0 by 4 phi I a by RQ. Integrating dl we get L, then 0 to 2 pi a, then we get v equal to mu 0 by 4 phi into I a whole divided by RQ into, in place of L we get 2 phi a minus 0, then we get mu 0 by 4 phi I a by R cube to 2 phi a. Here we get mu 0 by 4 phi, 4 phi here cancel out, here there's become 2 phi cancel out, and we get mu 0 to r cube into I a square. From figure we can get the value of r This is r, we can get r, and this is a radius of the circular coil, and this distance is x, as it is a right angle triangle, so r becomes root over of a square plus x square. Putting this value in that equation, we get mu 0 by 2 into, in place of r we put a square plus x square cube to the 3 by 2, as because r is equal to a square plus x square half, that means root over into I a square. That is the final value we get. It is the net magnetic field intensity at V due to the circular conductor. And we can get also at the center of the circular coil the magnetic field intensity. At center the magnetic field, and center the x is equal to 0. X is 0. Putting the value of x equal to 0 in the equation, v equal to mu 0 by 4 pi. In this, if we put this 0, we get v equal to mu 0 I a square by 2a cube. Then b equal to mu 0 I by 2a. This is the magnetic field intensity at center of the circular coil, and this is the formula for magnetic field intensity at the axis of a point on the axis of a circular current carrying coil. I think you must understand. And sometimes question arises why we could not take this angle. We take this angle as theta and this angle as alpha, because these two angles are different, so we take this theta and that as alpha, because theta is the angle between dl vector and r vector, and alpha is the angle between r vector and x. Thank you.